I want to tell you, a little bit about myself and the work that we do and how it fits together into broader context. And so essentially, I'll talk about how magnetic materials really are important in the evolution or revolutionary developments of information technologies. So, but first, here's the brief outline of what I want to talk about. I'll give you a brief view from my end, what life in a national lab is like. And then thereafter, I will talk about how you use magnetism in various ways, how some of you may trust your life to what's being done with magnets. Then I'll talk about our research, how we electrically want to control magnetism. And at the end, I will briefly talk about how magnets are being used to emulate living kind of functionalities. Okay, so I'll hope that should be interesting. So here's my own brief history. I'm originally from Germany. I was born in Cologne. You see here a picture there. It's most well known for a large cathedral there. I did do my undergraduate education in Germany at the Rheinisch-Westfälisch Technische Hochschule. So it's RWTH Aachen, where I got my diploma degrees in physics. But then I did my graduate education at UC San Diego in the US, and I've been stuck in the US ever since. But after being at UCSD, I started off as a postdoctoral researcher in the Los Alamos National Laboratory, which is in New Mexico. And 2 years later, I joined the ARGONNE National Laboratory, which, as Pam mentioned, is about 2 hours north from here, just in the southwest suburbs of Chicago. And I've worked there, 18 years, and the last 5 as the senior group leader for the group working on magnetic films. And then last year, I came to the University of Illinois at Urbana-Champaign. So since I spent a good 20 years at national labs, we thought that maybe it might be a good idea to give you a little bit of an idea what national labs are about, because most of you are probably not as familiar with that. So broadly speaking, there are 2 major types of national labs in the United States. One is essentially run by the Department of Commerce. That's the National Institute of Science and Technology. They have 2 locations. One is just outside Washington in Gaithersburg, Maryland, and the other one is in Boulder, Colorado. And the driver for establishing this lab was essentially the Industrial Revolution. And so it was founded more than 100 years ago in 1901. And the main purpose of the National Institute of Science and Technology was to provide reliable measurements, that can be used, both for commerce, to making sure that you measure things in the right way when you sell them, but also for developing new technologies. Now, the other national lab system is operated by the Department of Energy. The Department of Energy actually operates a large variety of different laboratories, 17 different laboratories. And these laboratories, for the most part of it, came out of the Manhattan Project, which was in World War II, the project to develop a nuclear weapon. Now, these were founded then after World War II. That's when they officially became called a national lab. ARGONNE actually was the one that was called a national lab first in 1946, although arguably Los Alamos may have been the first real national lab in that it was developed as a campus for a specific purpose. Now, as I said originally, the purpose was to develop the use of atomic energy. But nowadays, their purpose is much broader. It's a broad range of scientific topics with lots of different facilities that they operate, large-scale facilities. I'll give you some examples of that. So looking at the Argonne National Laboratory specifically, the starting point for the development of the Argonne National Laboratory was actually an experiment that was done at the University of Chicago. It was called the Chicago Pile 1, which was the first nuclear reactor that sustained a real chain reaction. So here's a picture of how you can imagine that. This was actually done in the basement of the football stadium of the University of Chicago. It was pretty clear that that was not the best location for doing these type of experiments. And so this was in 1940. The following winter, they moved this experiment to a private forest preserve that was outside Chicago. It belonged to a manufacturer of caseless sausages. And so he had this private forest preserve where he hunted his specific deer. And that became then the Argonne National Laboratory. So the second reactor was built pretty much where the Argonne National Laboratory is now. And after World War II, the lab was then founded by Enrico Fermi to develop the civil use of nuclear energy. And in fact, Argonne then developed the first nuclear power plant in the early 1950s. But so nowadays it's a much more complex laboratory. As I said, it's just outside Chicago, so it's situated here. If you look at an aerial view, it is a little bit like a campus, although not quite as big as the University of Illinois. But you have certain major facilities that certainly stick out. The biggest building here, as it turns out, is the administration. Don't know why they always need big buildings. I used to work in this building right here, which is the Material Science Division. But there's a notable big building here. This is the Advanced Photon Source. It's a big synchrotron. So it's a facility that allows to generate very brilliant hard X-ray radiation, which then can be used for lots of experiments, studying materials, but also lots of biology and other type of experiments. So here you see some of the main facilities that you may encounter at Argonne. So this is the Advanced Photon Source, where you have electrons traveling at near light speed around a circle here. And every time when they bend around the corner, they actually emit X-rays. And so in these areas here, there are various experiments then set up that can use these hard X-rays. That's good for structure analysis. For example, a lot of protein structures is developed there. When they looked at structures for the recent SARS-CoV-2 virus, for example, a lot of this work was done at the Advanced Photon Source. But the range of experiments can really go from physics to biology to engineering to all kinds of things. Another large facility that I have worked with a lot is the Center for Nanoscale Materials, where they have a lot of specialized equipment to make really small scale material systems. So there's different lithography, but also chemistry approaches. Another large-scale facility that I actually didn't work that much with is the Argonne Leadership Computing Facilities, but there they have computers that are pretty much among the most powerful in the world. This one, Aurora, is actually not working yet. It's supposed to be online next year. But what all these facilities have in common is that they actually user facilities. That means that researcher from outside the laboratory can write a proposal and use these facilities for free. Essentially, the proposals will be judged by their scientific merit, and if the experiments are considered to be interestingly enough, you can come for free to these facilities and use them. Um, so that's one big part of what national labs do, is they make really unique facilities available to the large research community. But aside from that, they do have mission-driven research, which is not that much like, unlike what you see at a university, except there isn't an educational component. So you don't see students generally there. So the focus is much more on research alone. So if you're a young budding scientist, being at a national lab is actually excellent, because you can really focus on the research and get a lot of really good research done with resources that are pretty amazing. So for any of you that may consider a career in research, I would definitely keep that in mind once you get to the point where you got your PhD and want to do a different position. No, you definitely want to go directly to grad school, because after an undergraduate, the only positions that would be available are in the technical support. So it wouldn't be really a scientific position. And that's really a one-way street. I don't think it's very feasible then to go back and do your PhD. Okay. But one thing that, if you're interested in working at a national lab, during your PhD, you can certainly work with a university group that collaborates a lot with national labs and uses the facilities there. So especially if you work in an experimental group that does a lot of X-ray scattering, or X-ray experiments, or neutron experiments, that's then easily, starting point to make a connection with a national lab and work there later. But it's not a pre-requirement. So when I started working at a national lab as a postdoc, I had no connection to it before that at all. So I don't know if you're familiar with this, but this is a picture that was taken, a little bit, well, over 50 years ago, when the US had the Apollo program flying to the moon. And what you may not know is that the astronauts who were flying to the moon in this little capsule here on top of this large Saturn V rocket really entrusted their life to magnetic materials. And the reason for this is if you look at the guidance computer that was used during the Apollo missions, it had a couple of really new technological developments there. One, it had really one of the first computers installed that was based on integrated circuit technology based on silicon. But the other one was it had a magnetic memory installed, which was based on magnetic cores. And by passing wires through these cores, you could then read out the magnetic state of these magnetic elements. And in fact, the whole software for the guidance program was literally hardwired in these memory elements. You see here these individual wires going through there. This is what they call the rope memory. So by passing a current through these wires, they could each magnetic element into a well-defined state, which then they could read out afterwards with these cross-cutting wire systems. So this whole idea was based on a magnetic memory that was developed at MIT in the early 50s. And incidentally, MIT was the location where this guidance computer was put together. Now, by today's standards, this memory was really not that impressive. It took about 10 microseconds to read out an element. It was fairly expensive. There was $1 per bit. And each memory cell was rather large, 1 millimeter squared. And the reading mechanism was difficult. By reading out the element, you actually would destroy the magnetic state, and essentially by seeing if you change the magnetic state or not, that told you what was the memory in the first place. This is the reason why they had in this read-only memory these additional wires that would allow the memory to always be reset into a well-defined state. Now, this is essentially how this looked like. You had these magnetic ring elements. By having a combination of currents to 2 wires, you get enough magnetic field generated to switch the magnetic state. And then by passing 2 sensing currents through a different set of wires, you can then read out what the magnetic state actually is. Now, if you compare this to today's prevalent silicon-based magnetic memories, random access memories, clearly there have been fantastic evolutions in technology. This is what we know from Moore's law. Moore was an engineer at Intel in the 60s, and he predicted that every so many years the density and the cost of electronics would double, and this essentially happened from the 60s on to nowadays. So you see that these modern memories are much faster. So you have access times in the nanoscales. It's much cheaper. It's a quarter per gigabit. And in terms of size, it's of course also much more smaller. Now, one thing that's different from this memory was inherently non-volatile, so you didn't have to maintain electric power to keep the memory. Here it's volatile. You have to keep it electrically powered, which each of you know, if you lose power to your computer, all the information goes away too. This is just another view of this Samsung memory from top, where it's really tens of nanometers are the sizes of the structures. Now, besides these kind of working memories for computer, many of you may be more familiar with how magnetic materials are used for long-term storage. And so this is what many of you may know as magnetic hard drives. So they also started the development of magnetic hard drives in the early 50s, where at IBM, they developed this large system called RAMAC, and it's really large. So here you see myself next to it when I was visiting the former IBM research facilities. And so it weighed a ton. It could store about 3.7 megabytes, on 50 big platters. So that's, if you want to play, you have your music library on there, not too many songs fit on there. And also the access time was really fairly slow. It took like a second almost for each bit to read out. Now, but the principle was very simple. You had a polycrystalline magnetic material, and on these platters, you would spin them around, and so locally you would have a read and a write head. So while the material flies by, you can apply magnetic fields with this write head, which puts in specific magnetic configurations where the magnetization points to the left or to the right. And then when there's a transition from left to right, magnetization flies by, there are external fields that can be picked up with a magnetic sensor. And that technology in its basic form remains unchanged until today. Um, so if you look at today's magnetic hard drives, you still have polycrystalline materials. You have a readout that you move back and forth. But the main difference is that the crystalline grains that we use for storing magnetic information are much smaller, and it's fascinating how small they have become. So here you see a modern magnetic recording media with the individual grains, and if you zoom in, you can see the atomic lattice planes in each of these grains. So each atomic grain that stores magnetic information there has of the order of 10 to 20 lattice spacings. So you're almost doing this at an atomic scale. And if you look at the track where you write magnetic information, even here the dimensions are really impressive. You see, well, let me see. Oops, sorry. You see at today's storage densities, which are 1 terabyte per square inch, the areas where you store information are about 50 nanometers in width and 30 nanometers in length. So you read out these transitions with an accuracy of about 1.4 nanometers. And you do this within nanoseconds. You write this within nanoseconds, you read it out within nanoseconds. So it's really actually quite impressive technology. And there are still some ideas how to push this to even smaller length scales. But it is clear that eventually you will hit some physical limitations of these systems here. Now, the reason why these hard drive technology is actually very important to all of us is because it really enables the type of, the type of prevalent, ubiquitous access to information that we're used to, where we can use the internet to access data all the time, where we store data in the cloud. And what does it mean, storing it in the cloud? It essentially means you have like 3 different types of storage mechanisms by which you store the data. One are solid state drives, which are essentially electric memories, but they are not volatile, so you can switch off the electricity and still maintain the information. They are very fast, but the capacity is limited, and you can only switch them so many times before they degrade. So for lots of the longer term storage, you want to have hard disk drives. And so what you know as cloud computing really consists out of large server farms that have lots of these hard drives that you access through the internet. And then it turns out a lot of the long-term storage is still dominated by magnetic tapes because they have the highest capacity and the highest endurance, if you want so. But they are very slow compared to these other data. So if you Google information that is Googled a lot, it's probably stored on a solid state drive, so it can be moved fast. If you Google something that is not so often used, it's probably in a hard disk drive. And if you want some information that rarely is used at all, your server retrieves it probably from a magnetic tape like this. Now, it turns out that using information like this comes actually at a large cost in terms of energy. So I'm sure many of you have used Google, all of you, I'm sure. So what would you say, how many times on average per day do you do a Google search? Let's say 5 to 10 times. So all of you together, your use of Google then is sufficient to boil a cup of water every day, because the energy that it takes to make a Google search, you require about 80 Google searches is about the same energy that you need to heat a cup of water up to boiling. Now, if you look at this, this actually becomes really a problem, the overall energy usage of information technologies. If you just extrapolate the growth rate, how energy consumption has been gone, then you see if you use the current systems that are being used, you can extrapolate that about 2035 or so, this energy consumption exceeds what we produce in terms of energy worldwide. Now, if you hope that technology evolves better so that the energy consumption per information storage goes down by like 3 orders of magnitude, maybe we can push it out to 2050. Now, the good news is the actual physical limits are about 7 orders of magnitude lower than current, existing technology. So maybe if we stay clever about how we do things, we can push this even further. But it really is an issue that we have to pay attention to. And these kind of graphs essentially show you the same kind of information. This is for mobile electronics, so it's your laptops, cell phones, what have you. But the power consumption doubles pretty much every 5 years. And the same is true for the server farms that support all the information content that we are using. The whole equation is a little bit complicated if you break down what the different contributions are here. A lot of the energy consumption is related to the air conditioning to keep everything cold. But nevertheless, half of it is still related also just to the energy consumption of retrieving the data on its own. So unless we really change the way how we use information in technologies, we will run into serious issues in about 10 to 20 years, how this will be sustainable anymore. And this essentially illustrates this point in a different way. While many of you are probably familiar with energy saving kind of technologies like LED lights and other things, indeed, we are better at some of the standard electronic usage that we use for lighting and heating and what have you. But it's more than compensated by the increasing electricity that's needed to power all the consumer electronics that we are using. So there's something for you to have your work cut out if you want an interesting problem to research on in the future. Now, with this, let's see how magnetism can play a role. So electricity and magnetism are really very fundamentally linked, and that we know for now almost 200 years, because 200 years ago there was a teacher of science, Hans Christian Ørsted, who discovered that electricity and magnetism actually influence each other. And so what he did is, at the time, he made lots of public demonstrations about the newest science topics of the time, which were electricity and magnetism. And then while he was doing his experiment to his public audience, he noticed that there was a compass needle on his table that moved every time when he put a current through a nearby wire. And he really didn't know what this was about, so he didn't tell the audience anything. So after his presentation, he went back in his lab and tried to figure it out. He actually couldn't figure out what was going on. So eventually he did write up what he saw and at the time in 1820, if you were a scientist, you had to write it in Latin, you know. So you're much better off these days. You can write it in English. And then Ampere ultimately explained what's going on, that if you have a current carrying wire, there's a magnetic field or that gets generated around the electric current, and this magnetic field can interact with magnetism. Now, nowadays, we want to actually combine electricity and magnetism in a very different way. And this is what's known as spintronics. And so the idea is the following. If you think about all the semiconducting electronics that you're used to, that you know, the way how this works is they're essentially based on lots of capacitors where you charge electronic charges on the capacitors a charge capacitor is one bit, a discharge capacitor is the opposing bit of information. And so in these electronics, you use all these electrons that you move around, but besides electronic charge, actually each electron has a small magnetic moment associated with it too. This is what we know as spin. And so the idea is, if we can now use in a clever way this magnetic degree of freedom in electronic materials, maybe we can do things in a better way and more efficiently. And so this basic idea of utilizing the spin degree of freedom in electronics actually gave rise to the Nobel Prize in Physics in 2007 from Albert Fert and Peter Grünberg. And I'll come back to that in a moment. But it allows to make now solid state magnetic memory where you encode information in how magnetizations in the adjacent magnetic layers are oriented, whether they're parallel or anti-parallel. And it turns out there's a whole bunch of new physics associated how the transport of electrons is related to these magnetic moments that reside on these electrons. And so I'll touch a little bit on these ideas. Now, before we do that, I want to get back at this point that if you look at a solid state material, the electrons in these materials come essentially in two versions. We call them spin up or spin down, meaning whether the magnetization points in one direction or another direction. And typically the two really don't interchange that much. Or in other words, the spin of an electron hardly ever flips into the opposite direction. So for electronic transport, the fact that you have two spin don't really seem to matter all that much. This becomes different if you have a ferromagnetic material. And so I don't know if you're familiar with an electronic band structure, but essentially the idea is that you can have electrons at different energies. And in a magnetic material, what you see is that you can have these electronic band structure also defined for different spins, spin up or spin down. And in a magnetic material, you have more of one spin direction than the other spin direction. And that's by having some of these bands partially shift with each other. So because you have more spins here, you have a net magnetic moment. That's the magnetization that you see. And indeed, this is how realistically a band structure looks like. This is a calculated band structure for nickel. So you see these so-called S electrons, which are symmetric in spin. And then you have these D electrons, which are these kind of lobes that are shifted in energy as a function of their spin. Now, this becomes important now when you look at the electronic transport in these materials. Because here, most of the transport is done by so-called S electrons. But how well they can transport the electron depends on the interaction with these D electrons. And so if you have no D electrons there, then you can transport current very easily. The resistance is low, you have a high mobility. If there are lots of d electrons at the same energy where you transport the current, then there's a lot of scattering, the resistance is high. Now this can be for either the minority or the majority spins. It just depends on where the so-called Fermi level lies. So that's just a technicality for those of you that are more familiar with Condon's metaphysics. But it gives rise to an interesting effect, which is called giant magnetoresistance. So if we have a layered magnetic structure that has more than one magnetic layer, then the electric resistance of these structures depends on the relative orientation of the magnetization in these two layers. So as I said, for one spin direction, the resistance may be low. For the other spin directions, the resistance may be high. And so if you have two ferromagnetic layers that have the same magnetization, then for the same spin direction, the resistance is always low. And for the opposite spin direction, the resistance is always high. So overall, a current that's carried by these two spin directions encounters a low resistance. But if you have now a structure where the magnetization is opposite, then it turns out for one spin direction, the resistance is low in one layer and high in the other layer, and the opposite is true for the other layer. So each spin direction will encounter a high resistance at some point. So overall, this combination of these antiparallel layers has a much higher resistance than these low resistance structure. And so this is what's known as giant magnetoresistance, namely that you can change the resistance a lot by up to 100% just by switching the magnetization in these layers. And so that was the basis for the Nobel Prize in Physics in 2007. And now you can use this in two ways. You can use this as a magnetic solid state memory, because if you can now engineer the system such that the magnetization here doesn't switch, but on demand you can switch this one, you can encode information in either low or high resistance. And this is really the basis for solid state magnetic memory these days. But you can also use this as a sensitive magnetic sensor. So if this layer here, the free layer, is free to react to external magnetic fields, then you can detect these external magnetic fields simply by measuring the resistance. And that's what you use in the read head of a magnetic hard drive to make magnetic hard drives as small and efficient as they are nowadays. Now, how can this now allow us to address these energy questions? So as I said, one of the problems with electronics is that it becomes very energy intensive. And with semiconducting electronics, the issue is, as you make the semiconducting electronics smaller and smaller, a lot of the useful currents go through the center of your device, and a lot of the unwanted currents go through the surface of your device. It dissipates into areas where you don't want it. So as you make it smaller, you just have much more unwanted dissipation over the useful currents. And that's why you have lots of power dissipation as you miniaturize electronics. Now, magnetism may help in various ways. So we can use it to use spin polarized charge currents. I mean, this is what happens in giant magnetoresistance, that the spin currents, that the charge currents carried by one spin direction versus the other become different. Then we can also think about how we use spin currents without having any charge currents. So we can imagine that by using spins that move in opposite direction, you can see that the charge remains the same always, but you still transport spin information from one side to the other. So maybe that's more energy efficient. Or you can even think of spin currents that are carried just by the way how the magnetization can get excited, where you don't move the spins at all, but you just have the spins pointing slightly in different directions, and these excitations can travel through magnetically ordered systems. So these are so-called spin waves. So all of these ideas may help to save energy in some ways. If you use spin polarized charge currents, you can connect your electronics directly to magnetic states, which can store information in a non-volatile manner. Just by being non-volatile, you can save energy. Or you can just process information in very new ways with new different type of excitations that may be more energy efficient. So if we go back to this giant magnetoresistance, here what we see is how the magnetic structure can change the resistance of your device. But it turns out, as we know from Newton, wherever there's an action, there's always a reaction. The same is true for these magnetic systems. If you pass a charge current through a ferromagnetic layer, which may become spin polarized, the spin polarized current can interact with the magnetization in the next layer and actually change the magnetization in this layer. And so you can use electric currents to directly switch magnetizations. And this works actually very well. This is the way how in solid state magnetic memories we do switch magnetic states these days. But there's a problem by using one ferromagnet first. It's fairly energy inefficient. You typically have a high resistive layer here that you have to pass the current through, and you need very large currents to be able to switch the magnetization, which can damage your device. It turns out there's a better way of doing this by getting magnetization out of the lattice of your materials. And this you can do via what's known as a spin-orbit coupling. Now this is what we call a Hamiltonian. It's the energy of spin-orbit coupling. All you need to understand is this gradient of this potential here is essentially the electric field that the nuclei of an atom generates on an electron. This P is the momentum of the electron. And so what that means is if the electron is moving in the presence of an electric field, this electric field in the rest frame of the electron looks like a magnetic field. And essentially, you can understand that moving currents give you a magnetic field. That's what Ampere figured out, 200 years ago. And so this magnetic field can then directly couple to this magnetic moment on each electron, which is this spin. So this is what this equation explains, and it is a relativistic effect. This is why you have these prefactors in front of it. Now, why is this important? If you now take a conducting material and you pass an electronic current through this material, then as these electrons move by an atom, they get deflected by the electric fields from the nuclei of these atoms. So your electron moves a little bit to the side. But what is important is it also sees an effective magnetic field, and this magnetic field has now spatial dependence. It's larger when you're closer to the nucleus because then the electric field is larger, and it's smaller if you're further away. And so now you have a magnetic moment that's exposed to a gradient of a magnetic field, And what that means is the magnetic moment wants to be attracted towards the direction of the larger magnetic field. So if the magnetic moment is pointing up, this electron is actually scattered a little bit more to the left. And if it's scattered, if the moment is pointing down, so opposite to the magnetic field, then it's scattered a little bit more to the right. So it's this spin-orbit coupling that gives a sideways scattering of spin-polarized electrons, where one spin direction gets scattered to one side and the other spin direction gets scattered to the other side. So you get an accumulation of spins on these sides. And so you can use this effect, which is known as a spin Hall effect, to then just inject spins into a ferromagnetic layer. And so you can manipulate this magnetization here in this way. And that's much more energy efficient because there's very little electric resistance here in between. There are other reasons why this can become much more efficient. And that's the new type of physics that we use for manipulating electric materials these days. And then we can read out the magnetization state here by passing a current perpendicular to this and read out the resistance of this whole stack. And so that's how a modern magnetic memory device actually works. Now, I want to briefly mention how this connects to the research that we are doing these days. At Illinois, and this REU program is organized through these Illinois Materials Research Science and Engineering Center, so I'm sure you've heard a little bit about it. There's one research focus where instead of ferromagnetic materials, we're interested in anti-ferromagnetic materials, where the local spins in the atomic structure are alternating in opposite directions. And so we are interested in how we can manipulate those magnetic structures with electric currents, how this magnetic structure changes electric transport. And we want to see if we can do many of the same kind of spintronics ideas with these metallic antiferromagnets. There are some advantages because they have no net magnetic moment. There are no magnetic stray fields. So two elements don't couple very much with each other. They are very insensitive to external magnetic fields. And the dynamics can be very fast, much faster than in ferromagnets for reasons that are a little bit complicated. So this is all encoding information in a local structure. But you can also imagine encoding information in different ways. You know, in a magnetic hard drive, you have information encoded into these domain patterns, and then you move the read and the write head with respect to these magnetic patterns to read the structure out. A different idea was developed 10 to 20 years ago, where we said, well, let's have the write and the read head locally fixed, but we move the magnetic structures with electric currents through a wire. And this is known as a racetrack memory. So you can do this in domains that really very much look like what you have in a magnetic hard drive. But you can also do this in different type of domains, which are called magnetic skyrmions. These are magnetic structures where you have locally magnetization pointing opposite to the magnetization in the rest of the wire. They can be very small, tens of nanometers. And so electrically, you can move them around and encode information in the presence or absence of these magnetic skyrmions. So I want to show you some of the research that we have done in this respect. These are these type of magnetic materials that can support these magnetic skyrmion structures. And so what you see here is an optical image of the magnetization. Um, if it's white, the magnetization is pointing towards you. If it's black, it's pointing in the opposite direction. And what we can do now is we can pass an electric current here, and by doing so, we can generate these magnetic bubble structures or magnetic skyrmions. So this is an electrical way by which we can, generate new information bits. And the physics is a little bit complicated. It has to do with the inhomogeneous currents that you have there. But it's not that different how you make soap bubbles. The physics is quite similar, actually. We are playing around in our lab now with structures like this, where we put these bubbles into wires like this, and then using an electric current, we move them around, down and up. And so this is one way how you can imagine using possibly, modern information technologies by moving magnetic structures around in your materials. Now, I mentioned that in some ways we want to look at how magnetism emulates life. This looks almost a little bit like an ant trail, right? Where ants moving along. But there's actually a different way how we can think of how magnetic systems may emulate life. And I want to very briefly touch upon this. The same kind of physics that allows us to manipulate magnetization like this also allows us to generate magnetic oscillations. If we put a large current through these magnetic systems, they start oscillating at microwave frequencies, gigahertz frequencies here. And this becomes very interesting, because if you think about how a natural brain operates, it operates with neurons that are stochastic oscillators, where once in a while they spike, and the synchronization of these oscillations is what gives us memory and which allows us to process information. And you can do the same thing with a magnetic oscillator. So by passing a current through it, you can get some oscillating behavior. And it turns out that using this magnetization dynamics, you can use for doing cognitive tasks. And so this is research that we do in our group together with this Energy Frontier Research Center on quantum materials for energy efficient neuromorphic computation. And so why would you want to do this? Well, it comes back to this energy efficiency business. If you think of very powerful computers like the supercomputer at Argonne, it has a lot of computational capacity, which is measured in flops. These are the operations, the floating point operations per second. Peta is 10 to the 15, so it's like a big number. But it also requires a big amount of energy, 13 megawatts. If you compare this to the natural brain, let's say of an Argonne scientist, then in terms of computational power, it's actually not that far off. It can do approximately as many logical operations. The amount of memory is lower, but it does this at 6 orders of magnitude smaller energy consumption. So the way how the human brain processes information compared to the way how a digital computer does it is inherently much more energy efficient. And the reason is twofold. One is by keeping a real digital information of the data costs a lot of energy to have a big energy barrier between what is a logical 1 and what is a logical 0. In the human brain, this is at much lower energy levels. And at the same time, in the natural brain, memory and processing is deeply intertwined, while in a computer, the memory and the processing units are separate, and moving this information back and forth costs a lot of energy. So the question is now whether we can use some of our magnetic materials to do computation in a way that's similar to how the human brain does it. And the short answer is yes. And this has been shown, for example, by taking spoken digit files, you process them and feed them into one of these magnetic oscillators as voltage signals. And then you look at the recorded trace and analyze them and what that means. So you look at the spoken file for when somebody says 1, and you want to see, can you recognize this as 1? So this is the voice recognition that you do with your cell phone, let's say, when you talk to Siri or something. And it turns out this works very well. Using this magnetic oscillator, you can get a 99% recognition, depending on how you process this data. Now, a lot of the work is done in the processing here. If you use a very good processing, you see that adding the oscillator only adds a little bit in terms of how successful you are at recognizing things. But you can see if you have a bad way of how you process the data, using this oscillator helps to increase the recognition quite significantly. So I know I didn't explain in great detail how this works, so if you have questions, feel free to ask me about that. But I want to leave you with essentially those key messages, that magnetic materials are really key to much of how modern society uses data. And by incorporating magnetic materials directly into logic, it may help to save energies in quite significant ways. And the basic science that we need to make this happen is we have to explore different ways how we can manipulate magnetism in magnetic materials. And with this whirlwind tour of the type of research that we do and where it fits in the grand picture, so the arrows that you see here indicate a local magnetic moment that could be on individual atoms or a larger region of atoms. But this magnetization can typically move around from one atom to the other. So it's a specific arrangement of spins that is free to move within the magnetic material. The topology of this spin arrangement is very different than the topology of a completely polarized state. What that means is that you cannot transform this spin configuration easily into a fully saturated one without doing something drastic. So it's like if you have a knot in a rope, only get rid of the knot at the end of the rope. And so essentially, this spin configuration is like a knot in the magnetic state, and so it becomes very stable.
Thank you so much. This is a really fantastic presentation. I learned a lot too. I had no idea it took 80 Google searches to, the equivalent energy of heating up a cup of water or something. Like I've never ever sat and really thought too much about the energy use of a Google search. That's pretty amazing.
Yeah, most of us don't worry about that.
Yeah, but it's a very important thing that we should be worrying about. So that really put something into perspective for me that I hadn't thought about yet. So yeah, cool. Awesome. Thank you so much. This was so awesome. Wonderful presentation. Thank you so much.